Thank you. We'd also like to thank our educational sponsors for the session as well, Alliance Cabrera, Knifeller, and Geo. So a little bit about myself. My name's Kevin Olness. I'm a PG. I work at WSP as a vice president. I'm currently the national director of the Emerging Contaminants and PFAS program. Fun facts about myself, their favorite sports teams. I have two boys, a 3- and a 5-year-old. They obviously keep me very busy. And you know, AFFF has become such a huge part of my professional life. It just so happened my hobbies make a nice acronym as well for DGGG, which is disc golf, guitar, and gardening. So our speaker, Stu Abrams, he couldn't make it, as I said. Unfortunately, he came down with illness. But Stu is he's a great person. He's an expert in PFAS remediation. He has a lot of passion when he speaks, and he provided us slides that Dora and I will be presenting for him. And I'd like to thank him for his contributions to this panel session. Our next speaker will be Gorm Heron. He's got the coolest picture out of the group. He's with TRS, the Chief Technology Officer. And I think, you know, when you're heating soils up to 5,000 degrees Celsius, right, for the destruction of PFAS, then you need to cool off and go do some windsurfing. So Gorm will be talking about a really cool case study that he did with some destruction technology at a DoD installations. And Dora Chang will be our other panel session speaker. I know Dora, she tackles problems with a purpose. And when you go after that problem, you're trying to find the solution, and you make sure that the R&D is there to develop the technology and make sure that it works efficiently before we put it out to the industry. So Dora's going to be speaking about some advanced techniques for remediation, some of the cutting-edge things that are going on in soil remediation. And she's with Jacobs, the global principal on PFAS emerging contaminants. And then Jim Cummings with EPA was very nice to sit here on the panel with us and address any questions and answers you may have at the end. So thank you, Jim, for joining us up here.
Actually, I don't even play a regulator on TV. I'm a technologist. So if you want to talk about MCLs or Circle 102 listing, I'm not your guy.
Yes, thank you. So into the presentation, the first topic we're going to discuss is the available and conventional soil remediation technologies for PFAS. As I said earlier, Stu prepared these slides. He couldn't be here, but the outline, we'll talk about the PFAS chemistry, little 101, so everyone's familiar with the compounds. I know a lot of people here are very familiar with this. The emerging regulatory framework for soils. We'll talk about excavation and disposal, landfill and incineration, capping and institutional controls, in situ activated carbon, solidification stabilization, both conventional and enhanced methods, and then discuss biosolids, which impacts soil. It could be a very struggling topic to deal with in the future because of how much biosolids are actually spread at agricultural facilities, which are, you know, up to 50% of them that are spread are done that way, and then that's at jeopardy because of the PFAS that's being found in them. So we'll talk about that some, and then some thoughts on that. So the basic PFAS chemistry, our favorite acronym here, per and polyfluoroalkyl substances. So there's a head of the compound and then a tail of the compound, and then the fully functional chain, a fully fluorinated chain, there has to be at least 2 carbons in the tail. So you have the head here and the tail there, and then the naming conventions are either the sulfonate group or the carboxylate group. The 2 most studied PFAS that we currently have the most information on are PFOS and PFOA. As you can see, there's 8 carbons in both of those compounds, with the PFOS being part of the sulfonate group. And then the extra carbon in the carboxylate group is in the head of the compound. So that's just a little 101 on the topic there. And then the chemical characteristics. So PFAS are surfactants. They love to party at the air and water interface, where the head is water soluble and the tail is hydrophobic and will be in the air. So the tails and heads that we just discussed, that's where they like to hang out. And the behavior at the oil-water interface is mainly due to electrostatic forces. The diffusion and co-contaminants and naturally occurring organics, it complicates fate and transport, especially in soil. And perfluorinated compounds are recalcitrant, which means they do not readily break down in the environment, and they're often referred to as forever chemicals in the media, and there's been a whole lot of articles popping up about that recently. Key issues for PFAS remediation: there is no magic bullet. There's not one technology that you can go to and say, this is definitely going to work for your situation. You have to evaluate your technologies, figure out what is best to do the remediation. The carbon and fluorine bond is exceptionally difficult to break. Bioremediation is almost impossible. I'd say there's some studies going on about that. But then the focus is presently on available technologies to immobilize and separate PFAS from media. Recent public policy actions, which Jim will not be discussing, as we made clear earlier, is the MCLs were finalized in April. So there's drinking water maximum contaminant levels for 6 PFAS. These MCLs are lower than any state or foreign country to date. They will also drive standards, most notably for groundwater and soil. And as you can see, the values here are very low. We have 4 parts per trillion for PFOA and PFAS, and it just makes everything such a challenge when you're talking about the parts per trillion levels. You know, they say 1 drop of water is equivalent, parts per trillion is 1 drop of water of 10 Olympic-sized swimming pools. But we're here to talk about soil, so let's back up dozens of trucks filled with silts and clays and sands and organic material and dump it into that clear pool, and that's the matrix that we're trying to deal with and discuss in this presentation. So other public policies is the designation of PFOA and PFOS as hazardous substances under CERCLA. This requires notification of releases. We did some calculations just the other day, and it's 1 pound of material, 1 pound of PFOA or 1 pound of PFOS that has to be reported, and that's about equivalent to 13 gallons of AFFF concentrate. So there could be a whole lot of reporting to the National Center based on those values. Their Phase 1 assessments have to include PFOA, PFOS, and then also the interim guidance for PFAS disposal and destruction, the EPA updated in April. That's the go-to document that gives you guidance where you can get rid of your PFAS-containing materials. And also for the DoD, there was a guidance that was updated in the summer of 2023 that gives direction on where your IDW and other PFAS-containing materials can be disposed of. And then the proposed RCRA, hazardous listing, that was in February and is expected to be finalized in 2024 as well. That requires corrective action requirements at hazardous waste facilities, and that could also impact where you can get rid of your PFAS-containing material in the future. So these are all new regulations from EPA, which are really steering our industry here in PFAS and remediation as well. So, Dora, I'll pass it to you for the remediation considerations.
All right, very happy to be here. All right, so when we talk about PFAS treatment in soil, first of all, we know PFAS are everywhere. They are ubiquitous, being used since 1950s. There's very chance when you go out and decide to collect soil sample, you are going to find it. And when you find it, doesn't really mean you have a specific sources that associate with what you detect in the site. So because of its how ubiquitous that is. So when you have any detection, normally we suggest you start thinking about the risk. The risk about a PFAS is not just about the PFAS chemical itself. It also associated with exposure pathway, how long you're exposed to it, and also the migration pathway, and whether there's a possibility the PFAS in soil can migrate down to groundwater, and groundwater being considered as the source of drinking water. Of course, also the duration. So when you talk about the criteria for PFAS treatment, a lot of times you start thinking about the exposure pathway. If that exposure pathway that you know of is mainly because of the construction works, because of the protection of on-site workers, you may look into a set of criteria more higher considering the migration into groundwater. So that is a risk level you have to think about. Once you confirm there's a risk, there are different dimensions you have to think about in terms of how much you want to do it and what kind of technology you decided to choose to remove or remediate soil. So when I talk about soil treatment technology, I can put them into 4 different buckets. The first bucket is time critical. You definitely need to remove the soil immediately, and because to cover up and remove and mitigate your risk immediately. And that normally is you dig out the soil with the known dimension, and you think about the offsite incineration and offsite landfill. The secondary is actually the same bucket is to consider the risk is not that high. Maybe I can consider the land management. Instead of digging it out and push offsite, you may do some kind of on-site in situ application. The third category is you do have the risk, and then it's not feasible to ship offsite. You may consider the on-site treatment technology. You still dig out the soil, but you use some kind of technology to separate PFAS from your soil and then reuse the soil that you treated. The first bucket is still under research and development. I'm going to talk about it in the second part of this presentation. Is start thinking about directly destroy PFAS in soil directly. And offsite landfill or the on-site in situ management or on-site separating PFAS from soil do not directly destroy PFAS. Incineration is. So let's think about incineration here on this slide. You mentioned a temperature. Because our carbon fluorine bond is so strong, you definitely need a very high energy in order to break that carbon fluorine bond. The question is there are so many carbon fluorine bonds associated with PFAS, do you actually completely break all the carbon fluorine bond? So that is where your research development it is. If it's incomplete destruction of the PFAS, what kind of intermediate product can be generated? What is the end of the day, end of the PFAS life cycle? Do you actually solve the problem or create more problem to solve? So that is why there's a reason that DOD currently banned the offsite incineration. Offsite incineration will require very high temperature, more than 1,000 degrees C, and the time of the incineration is also critical. So it's between the time, between the temperature, that make the cost very high, and not just about cost itself. We also run out of capacity doing the incineration of the soil. So there are multiple different factors you have to consider when you consider incineration. All right. So this is the options I'm talking about, the on-site and in situ land management, meaning you do have the PFAS in your soil. However, you figured out you don't have the capacity, you don't have the cost, your risk profile doesn't really justify to dig out every molecule off of the ground. And then for the treatment, in this situation, you may consider in situ applications. For the in situ application, you are not actually removing PFAS. You are actually stabilizing. So the immediate question is, how stable is stable, right? Is it possible over the long time your PFAS can leach out? So that is where the people focusing on R&D figured out what kind of chemicals they can bond PFAS very strongly and minimizing or completely mitigate the leachability of PFAS off the soil. The duration of the stability, right? So that is really the areas that people start thinking about what kind of chemicals they can have a very strong bonding to the PFAS and remain in place. But once again, your PFAS still in there. So it still represents some kind of risk for long term. In terms of chemical selections, there are commercial products available. Normally, you mix in 2 to 5% of your chemical and bond it with PFAS. The question is, PFAS is a very wide range of chemical. It has short-chain PFAS, They are more mobile, high solubility. You have a long-chain PFAS. They are more stable, easy to be stabilized. And you also have some volatile. You cannot really have one chemical solve all the problem, and that is why you have to prioritize your risk, prioritize all your costs, and also prioritize the life cycle. What is your data objective? So biosolids is actually showing here, like I mentioned, PFAS are so ubiquitous, a lot of time you are not able to find or identify specific source that contribute PFAS in soil. Biosolid is really a problematic area because biosolid doesn't have its really have the beneficial reuse, right? Because it's rich in nutrients, rich in organic contents. You often go to the Home Depot and buy a bag of fertilizer or compost and apply in your backyard. Very, very likely the bag of a compost may contain PFAS. We don't know. There is a possibility to contain. So over years, when you have land applications all over the places, they can become your source of a PFAS. We don't know the levels, and the composition of PFAS in fertilizer and compost normally are different from HFOF. You may be able to do the source identification to differentiate both. So some general thoughts. PFAS soil treatment are not really, in terms of R&D understanding of technology, are not as advanced comparing to water treatment, simply because we always like to start with something which is easier to be understood, which is water metrics, right? And soil is a little bit behind right now in terms of commercially available technology, are mainly focused on the sorbent selection that can bond or stabilize PFAS. And landfill and incineration capacity will eventually limit it. Another concern is actually environmental justice, because our landfill incineration are normally located in the low-income communities. They will be directly exposed to and get under the risk of taking any kind of PFAS from the air emission or from the landfill leachate or groundwater impact. So biosolid, I just mentioned about it. I think that will be a growing topic down the road in terms of the impact of PFAS in biosolid, how they being then applied, and the strategy in terms of remediate PFAS in those kind of materials. So I'm going to give my time to Gorm to start talking about thermal treatment. Thermal is also one of those buckets you're thinking about separating PFAS from the soil. So Gorm.
Can I say something? I can make a couple of remarks before we get started. Is that me? Anyway, if you're going to consider stabilization solidification, you need to think about your net testing method. There are a number of methods out there, the TCLP, the SPLP, but I'd recommend that you pursue the LEAF method, LEAF method, which seems to be gaining some popularity for testing stabilized solidified materials.
Okay.
Oh, actually, there's one other point. I don't think we're going to necessarily clean soil to the 4 parts per trillion. Anybody in here who doesn't know about CERTA BSTCP, the DoD program that really is the only game left in town for technology development? They have, I don't know how many, 4, 5, or 6 projects right now trying to determine the leachability of PFAS under different hydrogeological regimes. So the point is, I don't believe we're going to end up cleaning soil to 4 parts per trillion. It's got to be a number higher than that, depending on how these air-water interface and soil leachability numbers and research plays out.
What a build-up to my first case study where we actually tried to do that. But thermal treatment, of course, has always been a very powerful solution for source areas. Typically, chlorinated solvents has been most of what we've done. Arcadis wrote a summary paper a few years ago, summing up 650 in situ thermal projects. So the thing about realistic and affordable, it's not cheap, but I can tell you we had 650 clients who actually paid for the thermal remediation, and if they had a cheaper option, they would have done that. So it's not affordable everywhere, but there are fits for this technology where it is the lowest cost solution. And 650 projects and clients would not have occurred if that was not the case. So we just have to show that it's safe and practical as well, and we're in the process of doing it. The first thing you look at when you have a new group of chemicals is essentially how hot do we need to treat the soil? What are the boiling points of the contaminants? And you see on the left-hand side here, you see traditional targets for thermal remediation from TCE at the bottom with a lower boiling point, only 87 Celsius, all the way up to some PAHs and dioxins there, around 350. Those are all contaminants we have so much experience with out of those 650 projects. So if you can compare the PFAS boiling points to those known contaminants and what we did for them and what temperatures it took, you have a really good idea of what temperature you have to get to for PFAS soil treatment. And it's in the 300 to 400 degrees Celsius range, not 5,000, but you were close. So the first thing we do is we take some difficult soil, spike it with a lot of PFAS, wait a while, and then we do bench testing on it. So we take these columns of PFAS impacted waste, in this case with a really high starting concentration of 22 milligram per kilogram, as you can see the left bar there. Then we heat it for a couple of weeks at different temperatures, 300, 350, 400. And you can see here at 350, we get really good reductions. At 400, we get complete removal of all the PFAS compounds we were looking at here, the targeted PFAS compounds. So based on this initial laboratory study, it indicates you can get most of the stuff out at 350, but 400 you get to really basically non-detect for PFAS, or the 4 parts per trillion if you have to do that. So when we head into the field, we're looking at in the temperature range of 350 to 400 degrees C. The first demonstration we did for ESTCP was at Eielson Air Force Base. They have 51 of these soil piles with PFAS. And they've been up there for decades looking for a solution. There's not a landfill that could take it in Alaska. It would have to be driven very, very far. So they just didn't have a solution in the state that was realistic and practical for them. So this is one of those 51 stockpiles. It's underneath that cover you see there, and the pipes sticking out are all 3-inch diameter carbon steel casings that we've driven into the soil without touching the soil. And they each then get a little heating element. It's called thermal conduction heating. We have electrical equipment that puts power to each one of them, makes them glow, and each of those metal pipes become a little glowing stick in the soil. And so when they do that for about 3 months, the soil reaches the temperature of approximately 400 degrees, and we have extraction pipes in the pile. In this case, we had 4 different extraction wells in the soil, and we apply a vacuum. And without touching the soil, we basically heat it up and vacuum the PFAS out. So that's what it looks like when we were building it. A month later, it looked like this. Now it's got Alaska weather, and we have a little tarp over the area to keep the snow from covering everything and melting on top of it. And in there behind, in the dark, you see the heater heads and everything. And in the foreground, and transformer and some of the electrical gear that it takes to heat up. So we reached the target temperatures in the soil while it was minus 30 Celsius on the outside. So insulation does work, and it is realistic to do it even under those climatic conditions. What comes out has to be treated. We chose not to try to burn the vapors because of some of the issues Dora was mentioning with high temperature, this and that byproducts. It's an incomplete science. So instead, we cooled off all the vapor that came out, condensed the water, the steam into water, and then we treated the water with carbon, and we treated the vapor with carbon, and PFAS likes to stick okay to both of those. So basically, the only little waste that we had with PFAS in it was the vapor phase carbon and the liquid phase carbon from this, a few 100 pounds. soil temperatures in the pile itself. You can see the scale on the left is it's 450 degrees at the top, and these are average temperatures at 4 different locations in the pile. You see how we approach 400 degrees towards the end. So the cooking process itself was satisfactory. Then we stop the heating and we wait a little bit, and then we take soil samples across the pile. We took, I believe it was 16 or 20 different soil samples. And you see here, you see them with the red bars representing starting concentrations and the blue final concentrations after heating. If you look at the one all the way to the right, it had the highest starting concentration, and it was basically non-detect afterwards. That was one of the samples that easily reached 400 degrees. We had a few of them that were at the top of the soil pile that only got to 350, and they represent some of the blue bars that still have a little bit left. At the end, our average soil concentration in a pile was, funny enough, Jim, 4 parts per trillion. Or 4.1, actually. So that was very encouraging. It let us propose to ESTCP, we can do this above ground in these piles. We can probably do it in situ as well. So here is our next project at Beale Air Force Base. It's an old fire training area that had extremely high soil concentrations of PFAS in the topsoil. We basically did the same process. Here you just have in situ installation of heaters. You have an insulated cover on top. And I'm going to show you the results in probably the worst slide I have. It's the busiest of the slides I have, but I'll try to explain it. On the left, it's before heating. You see different contours of PFAS concentrations. The red is roughly over 2 milligrams per kilogram. That's the orange blob, and the green is between, let's say, 0.1 and 2 milligram per kilogram. So still very, very high. The green sticks are temperature monitoring locations. And so that's the pre-thermal concentrations. On the right, you see what we found after the heating process. And you can see in the hottest area, the areas to the left, you have no color. That's where we've removed, and we reached temperatures of about 400 Celsius. We removed all the PFAS, essentially, down to non-detect concentrations. And on the right-hand side, you see small concentrations remaining. What happened was and we've shown this with energy and water balances, is that we actually had some purged water that ran underneath this vapor cover you see into the treatment zone from one side, from the eastern side. And we extracted 4 times more liquid water from this area than was there to begin with. So all this other water came flowing in. Where the water table is 50 feet deep, this was happening at 4 to 5 feet below grade. So rain at Beale Air Force Base, which is not very typical, but had led to purged water that kept flowing in. Lesson learned is next time we go out there 6 months before and we cover a larger area, pave or otherwise stop infiltration, and then we just don't allow that rainwater to become purged water for a long period, then we do the process and we won't have that infiltration issue. Final slide is our current project. We're turning power on this week. This is at JBER, another Air Force base in Alaska. We want to be certain not to rely on groundwater, purged water flow. Well, you can treat the soil above grade, and we're doing that in this DIU demonstration. There will be 2,000 cubic yards of PFAS impacted waste here, targeting again 400 degrees Celsius. And as I said, we turn the power on this week. Just a few comments about, is it affordable? Is it realistic? Well, you can see the energy that we need here, 500 to 800 kilowatt hours per cubic yard, or 4 to 700 per cubic meter, 4 to 700 per cubic yard. So the energy itself is not really cost prohibitive, right? That's like $40, $60 for each cubic yard. But the rest of the process, of course, costs something too. So we're hoping we can get down in the range of $500 per cubic yard when everything is said and done, and we're treating large volumes. In some places, that's not affordable. If you have a cheaper option to go to a landfill in Utah, if you're in Utah, you're probably never going to do this. But if you're in Alaska, it'll cost you 3 times more to transport the soil to another facility. So again, this whole thing about affordability, and by the way, also sustainability, is it sustainable, depends on where you are. Something can be highly sustainable in one state and not in another, depending on where your energy comes from. Is it from wind farms? It might be really sustainable from an energy standpoint, but if you're burning coal, it may not be. So that was my final comments for this. Thank you.
We definitely want to make sure we have a Q&A to end of this session. So, all right, I'm going to talk advanced PFAS treatment. I'm going to fly through those technologies very quickly. The first one I'm going to talk about is soil washing. I mentioned about 4 different buckets, and one of the buckets is you dig it out and do the on-site separation of the PFAS from the soil. So soil washing is one of those kind of technology, and the purpose is trying to separate and remove PFAS out of the soil. And soil washing, I hope you all agree with me, kind of a technology retired over years in the States. We don't do soil washing quite often for hydrocarbons, for chlorinated solvents. Bring back to the table because of PFAS. And the technology that can separate PFAS out of a soil metric is very challenging and very difficult. So there's a full-scale demonstration of soil washing in Australia that we all learned about, and there is some ESTCP field demonstration right now, I think, using the soil washing technology to try to understand the cost, affordability, feasibility, that kind of stuff, and what kind of wash solution that we have to apply. As you can see on the slide, for soil washing, it's not a simple solution. And there are many different steps in terms of separating the fine materials versus coarse material. You have to wash PFAS off. The washability of PFAS may vary depending on the chemicals. You may need to wash it several times. And then the most important thing is you are going to generate the wash effort, which is the wastewater coming out of the process laden with the PFAS that you need to follow up with some kind of a treatment. So as all we know, a lot of treatment technology associated with PFAS will generate solid waste and liquid waste. So this is definitely belong to that kind of category that you will have the solid waste, liquid waste generated while you are meeting the objective of removing PFAS from your contaminated soil. So it's not a simple solution. Some other polishing technology, secondary treatment technology need to go along with soil washing technology. So definitely it's not a cost-effective approach. But it's still, the understanding of it is still needed because our technology right now in terms of on-site treatment is so limited. In addition to thermal, I guess the second one is soil washing. And remember I mentioned about there's a fourth bucket, it's a PFAS destruction. So I'm going to go over the PFAS destruction. There's only one, maybe there are more than one, but I'm going to mention about ball milling. Ball milling is a technology people trying to understand whether we can use a mechanical force to break that carbon-fluorine bond through the ball milling process. So it's still under R&D, but this is a technology directly trying to destroy PFAS in soil. So you dig it out, put into the ball milling reactor, grind it aggressively, and breaking down the carbon-fluorine bond so you can remove and destroy PFAS, not just removal, separation, you actually destroy PFAS, and hopefully that treated soil can be reused on site. And as I mentioned, most of the soil treatment technology, you are going to generate some liquid waste and solid waste, including GAC, ion change resin. You treat the wash wastewater coming out from the soil washing example for soil washing technology, or using those sorbent to remove PFAS in the vapor condensate from the thermal treatment. regardless if you have those liquid waste being generated, there are some destruction technology already being available, at least demonstrated, to destroy PFAS in the liquid waste. Those liquid waste technology can include electrochemical oxidation, plasma, HOLT, or reductive UV sulfide technology. Those technologies belong to the liquid destruction technology. I'm not going to go over too much. And this is the impacted, this is for the ball milling technology. Graphically, you can see you pretty much just feed your soil into a ball milling machine. So what you will do, you will see a lot of stainless steel balls, right? Actually, they rotate, and then they grind the soil accordingly, and hopefully they generate enough of the energy to break that carbon fluorine bound. So you can see on the left-hand side is a bench scale study of using the ball milling to destroy PFAS. It does remove a significant PFAS or destroy PFAS in soil. However, it did not really achieve microgram per kilogram unit or even parts per trillion units. More research will be needed. Maybe likely it will require some kind of a chemical amendment to enhance that destruction. And the middle of the figure is kind of like a small laboratory scale ball milling, and the figure on the right is a pilot scale mobile unit. So I want to introduce very quickly in terms of supercritical water oxidation, and this is a technology being present in our industry for a very long time. Commercial large scale is already available. However, right now we are looking for a new application using this technology to destroy PFAS in HFOF in liquid as well in solids. The key is trying to create that supercritical point that everything will become, a lot of magical things will happen. A lot of destruction technology will take time, the residence time, in order to break that carbon fluorine bound. This technology, we talk about seconds. So once you reach that supercritical point, biosolids, microplastic, PFAS, spin ion change resin, spin GAC will completely mineralize. Mineralize converted into fluoride, converted into water. There's no solid remaining out of that supercritical reaction. So that is really a fascinating technology. This is not new. There are 3 different companies now looking into this technology for PFAS destruction applications. Those companies included 374 Water and General Atomics and Revive. So those 3 companies does have their own reactor design. They are not identical. And currently, they all demonstrate that HFOF can be destroyed, liquid waste can be destroyed. In terms of solid destruction, right now, it's 374 Water probably has some demonstration. That is what I'm going to show you. So this slide is kind of like, you can call that a pilot system. They use 1 cubic yard per day kind of a reactor, trying to destroy spin GAC and spin ion change resin. We all know GAC and ion change resin technology are promising technology for liquid treatment, right? So you are going to generate those spin ion change resin and spin GAC. Normally, you have to ship off-site for incineration or landfill or reactivation. This idea is bring that destruction unit on site, and you will destroy GAC and ion change resin completely. So you can see on the photos, that probably is to highlight that you can see the GAC ion change resin slurry in the testing tube. And after scroll treatment technology, your GAC mineralized, ion change mineralized, your PFAS mineralized as well. So this is actually effluent coming out from the scroll reactor. And you can also see some of the data. The font size may be too small. But you're talking about milligram per kilogram of PFAS in the spin media and come out the effluent containing low parts per trillion of PFAS. Just remember, you come in as solid, come out with liquid. So that is a very interesting study, and then currently there's a field demonstration funded by Air Force to confirm the mass balance and also do the field larger scale demonstration. Gasification is one of WSP's CERTA project, and very similar concept. You try to use a thermal process to destroy spin GAC, spin ion change resin, as well as PFAS. But the benefit of this technology, it does generate some products that can be beneficial reuse, which is biochar. And scroll is wonderful, but really you leave nothing out of that whole process. Nothing will remain that you can reuse. So gasification does have that benefit. You will generate biochar. So there are multiple technology that are kind of go into like a field demonstration phase, which is very exciting in this industry, seeing how PFAS really being challenged to destroy. And those are technology, once again, a liquid waste. It can be used for any kind of upstream coming out from the soil separation technology. Those technology including electrochemical oxidation, plasma, hold, UV sulfide. The goal right now is kind of understand the mass balance, whether those technology completely break down the carbon fluorine bond, what is intermediate, or whether they are in any intermediate generated from the destruction process. So what takeaway, if you kind of start thinking about, I want to do the on-site treatment technology to remove and separate PFAS from the soil, you definitely need to think about the treatment train approach. So when you have a site heavily contaminated by soil, by PFAS, you may be thinking about the bucket number one, I'm going to do the time-critical removal, dig a hole for incineration or landfill. And then the second bucket, I'm thinking about their high-risk soil. I put it out to do the on-site treatment. And third bucket, some of the lower concentration, lower risk profile, I may consider in situ stabilization. All right, so those are the things I want to highlight. And always there are more research to do. Always more research is needed. Definitely we look into some nature-based solution, low cost, more sustainable, because a lot of those technologies I'm covered today are very intensive in terms of labor, energy, and cost. So I'm going to stop right here, and Kevin, you're going to moderate the Q&A. Thank you.
Kevin, could I interject? Could I?
Yes.
Interestingly enough, highlight a couple of the points that Dora made. One, supercritical water oxidation has recently been deployed full scale to treat landfill leachate in Grand Rapids, Michigan. So if you have a landfill that's got a leachate problem, it's a candidate. The bad news there is they've solved the corrosivity problem of their AFFF and other materials, but they have a problem with the abrasiveness of soils. So I beg them every week to figure out how to treat soil. But at the moment, the SCWO folks will only say that they can handle pumpable slurries, whatever that means.
Yes,
so
it is.
Again, as a Superfund guy, I need somebody to treat dirt. The other point I'll make is on the electrochemical ball milling. I think it was embedded in one of Dora's slides, but the one project we looked at was actually electrochemical ball milling, where they're adding a chemical additive to try to improve the PFAS destruction. So,
Thank you. Thank you, Jim.
Thank you. So we're going to take questions from the audience. If you have any questions, please go to the middle of the room to use the microphone. I don't see anyone lining up yet, so I will get the Q&A going. So we went through all the different soil remediation technologies, some advanced, some traditional, the great case study you did. What, in your opinion, what is the most cost-effective method that's currently available to us?
Well, the most cost-effective, of course, is in situ stabilization and solidification. That is for sure, and the unit cost is way significantly lower. But we do need to know that basically you keep your PFAS in place. It's a risk reduction, but there's no risk removal. So definitely there's pros and cons.
And Jim?
well, I've spent the last 20 years trying to stop doing pump and treat because it's so thermodynamically inefficient, but I'm afraid we're heading back that way, at least for the near future. And anyways, for those who've been around a while, you know that ISCO and bio are two of the more prevalent in situ remedies. And again, embedded in one of Dora's slides was the suggestion that that's not going to work for a while. ISCO in particular, it doesn't do very well on PFOS. It does okay on PFOA. And it generates daughter products that are more mobile and soluble, whose toxicity is largely unknown. So, and also, historically, we used to think of sources, right, as 10,000, 20,000 parts per million. Hotspots for AFFF and PFAS are going to be much lower than that. So you're going to have to recalibrate the way you think about your sites and what you're trying to deal with.
Thank you. You want to talk?
I have a pretty high cost solution, right, the thermal solution, but it may in some places be the most affordable. Cost for doing PFAS soil treatment are similar to cost for doing dioxin remediation, dioxins and furans. And at the moment, for instance, USAID has done the project in Da Nang Airport where 113,000 cubic yards were treated at the same temperatures that we need for PFAS. So that was a good cost-effective solution for them. So there will be some cases where the thermal option is the most affordable, but they're rare. It's like 1 out of 10 maybe of the projects.
Okay. Thank you. You can go ahead.
Hi. So I studied supercritical water oxidation about a year ago, and at the time, the highest rates the processing rates were maybe on the order of about a gallon per minute. And I also, the treatment of AFFF required significant amount of dilution. Have those problems been, have there been improvements in those two areas? Thank you very much.
Thank you.
So I did highlight the benefit of scroll, but scroll definitely not perfect there. I think Jim mentioned a little bit in terms of the understanding of AFFF destruction. Yes, dilution is actually needed. I'm not familiar in terms of the best optimum condition for AFFF destruction, but if there's any thought, there's definitely corrosion issue. Some companies have better understanding to control that. Some companies are kind of a little bit behind. So it is still, a lot of things to be understand. Definitely talk to the vendor and have a good control and understanding what is actually in your feedstock. So dilution sometimes is the solution to make that corrosion issue resolved. But understand your geochemical condition, water quality is definitely the needed things to do.
Actually, the practice is going the other way in the following sense. Because of the relatively low concentrations of PFAS in water, almost all of the SCWO applications now are involving a concentration step using SAF, surface active foam fractionation. So landfill leachate, they think they're getting 10 to the 4, 10 to the 5th concentration factors. They think they can go up to as much as 10 to the 6. So my point is, the conventional, the practice now is treatment trains, significantly concentrating the PFAS stream before you subject it to the destructive processes.
So the dilution is really to eliminate the side effects associated with scroll. But Jim is right, and there's no limitation in terms of the concentration range that scroll can deal with, as high as you can imagine, because the chemistry, the reaction is so strong, you will break down PFAS fairly reasonable, I would say, very quickly.
And I'm sorry, please finish. The other point is, when the SCWO folks first started out, they were kind of in a batch or semi-batch mode. And we've emphasized to them the importance of being able to operate in a continuous or flow-through mode to get the kind of economies that you can achieve. So my suggestion would be to contact one of the SCWO vendors and ask them what their current throughput is. Again, the 50,000 gallons or so of landfill leachate that they've processed in Grand Rapids, my point is they should be able to provide you with a throughput number that is based on actual field application.
Thank you. Go ahead, Jim.
Yeah, Jim Carter with EMAX Laboratories, also a member of the steering committee of the Environmental Community of Interest. So great to see such a great turnout here. My question is for Gorm. On one of your slides showing the breakdown with the thermal, the temperatures, it looked like there was one class of the PFAS that was not affected. It was very low level, initially and a low level after the treatment. It was hard to kind of understand that slide, but it looked like there was one classification that was not really touched.
That's surprising to me. I would have to look at the data again, but we haven't seen that in the analysis. And those slides didn't break down the individual PFAS, right? Those were individual soil samples before and after. So you may have noticed an area where maybe the starting concentration was low and it was still in the same range afterwards. So that's not a certain PFAS compound. That's just the total PFAS in that soil sample. But we can look at the data more closely, and if you want, we can talk about it after this.
No, I was just curious. So
Yeah.
there was a soil type that didn't have a reduction, or it was just so low?
Yeah, those were the shallow-most soil samples at the 2-foot interval at the Eielson Air Force Base demonstration, where temperatures barely reached 350 C. We took those same soils and gave them to Kurt Pinnell at Brown University, and he cooked them for another week at 400 and went to non-detect concentrations. So essentially that demonstration ended on December 20, so everybody could go home for Christmas. Had we had another week, we probably would have gotten those samples down also.
Thank you.
Thank you. You go ahead, please.
Morning, Bong Lee from NAVFAC Southwest. This question is for Gorham. On your slide, with the thermal where you have pipes sticking in the soil, I understand that cost, time, and efficiency still seems to be very high. Are you limited in terms of the quantity because of you need to spread the soil in such a, I don't know how many lifts or thickness, but would this technology be limited in terms of capacity and how much soil that you can treat?
Yeah. I really appreciate the question. So the demonstrations we've done so far have been fairly small because of ESTCP funding limitations, right? And the DIU, the last one, is bigger. When we treated dioxins in Da Nang, we treated 113,000 cubic yards in 2 phases with exactly the same technology, the same heater pipes, the same electric elements, the same target temperature. So that shows you that you can scale it up. Each batch was 57,000 cubic yards and was treated in about 6 months. So that's about as big as we've ever gone with this technology. I suspect most of the PFAS projects will be smaller than that, right? There will be the concentrated fire training area, topsoil probably scraped or excavated into a pile, treated above grade, where you eliminate the in situ challenges of shallow groundwater or purged water. And that just depends on the size. We could also treat farmland with PFAS in the top foot based on fertilizer, having had PFAS. We could scrape all that into a pile, treat it, redistribute it back out so the farmland could be used again. So who knows where all the cases will come from, but that's also an option.
Okay, cool. Thanks.
Go ahead.
Hi, I'm Christopher Carducci from University of Illinois, Chicago. So I saw that you had numbers up there, it's about 500 to 800 kilowatt hours per cubic meter. So is that the specific energy consumption for the thermal project? Was that a theoretical number? Is that experimental? Where did that number come from?
The number is 2 things. You can do it on a napkin without heat loss. You get 250 to 300 kilowatt hours. And then you add the heat losses to that, you typically double it. And for instance, in Da Nang, where the size was really large, we were in the lower end of that range. We were in around 500 kilowatt hours per cubic meter because we had small surface area to volume ratio. At Eielson, the little one I showed you was only 144 cubic yards, so that one had a lot more heat loss, and we were in the higher end of the range. So basically, theoretical, easy to calculate BTUs, calories. It's pretty simple. And then based on multiple field studies where we basically did the energy balance.
Understood. So is there... Okay. So is there an equivalent SEC for all of these methods that you showed in terms of like you can use electrochemical, things like that? How does the thermal method kind of compare? Like what's the specific energy consumption across all these methods? What do you think is the most efficient, at least in terms of actually breaking it down in a timely manner versus actual implementation? I would imagine it's much easier to scorch earth than it is to try to electrochemically break down a massive amount quickly.
That's a tough question, but I don't know if I can answer it correctly, but we did a case study basically and wrote a white paper on the energy consumption of thermal, and we compared it to excavate and truck it onto a landfill. Sounds like you use almost no energy for landfilling, right? But that's not true. When you include the excavator cost, the diesel for transportation, it was something like 200 miles you could transport the soil. And if you transported it farther than that, you've used more energy than to treat it in place with our technology. So just an example of what appears to be extremely energy consuming, because you see these red glowing pipes and you're getting to 400 Celsius. Include all the energy that's used for the people to and from the site, for the diesel, for the trucks. It may use less energy than even excavation and landfilling.
Awesome. Thank you so much.
Actually, if I could make one point on a previous question. It looks like for the technologies that Dora talked about, they seem to do better on the C8s, and the performance seems to be degrading a bit for the C4s and shorter. So if you're designing a remedy and the regulators are telling you which of the suites of PFAS they're concerned about, you need to be aware of the fact that the performance may vary currently based on the chain length of the PFAS compound in question.
We got one more question, and that'll be good.
Thank you. I could ask a lot of questions, but I'll try and be quick. Agricultural risk. You mentioned PFAS in fertilizers getting out there. My question is, has there been testing on any of the produce from those fields, and how bad is that? And assuming that it's sucking up PFAS, is there a way to use plants to remediate the soil?
I can answer. Go ahead. Go ahead. It turns out there are a couple of papers on phyto, not looking really great because you got to do something with the phyto materials afterwards, and you're probably going to have to apply it over 4 or 5 growing seasons. So that's a partial answer to your question. And I'm not sure it's the pesticides or whatever that are contributing to the loadings. I think it might be areas where biosolids have been applied.
Also, for the uptake, PFAS uptake by the produce, very associated with the specification of the PFAS. So if you have a long-chain PFAS, likely you will stuck to and being uptake by the roots. And if you're talking about getting to the leaves, more likely the shorter chain PFAS will uptake to the leaves, which are less bioaccumulative comparing to the long chain PFAS. So depending on the produce you're talking about, but yes, there are some publication about the uptake of PFAS into produce.
And just to explain that this is not a theoretical problem. For instance, in the state of Maine, they surveyed the blood serum levels of a whole lot of farmers to see if they got exposed from farming, essentially. One of the guys, Adam, bought a farm and farmed it organically for 7 years. It turns out that he had biosolids on his land before he bought it, and his level is now 1,000 times the average, coming from eating what comes off the farm and drinking the water from his wells. So the problem is real.
Okay. Thank you.
And it also turns out, as we were talking before, the longer chains seem to be closer to the surface, whereas the shorter chains seem to migrate a bit further downward. So that's another issue to be addressed in dealing with potentially contaminated farmland.
Thank you. Well, we're at our time. I'd like to thank Dora, Gorm, and Jim. You did an outstanding job.